Hi. I think this might be the last one, at least for now. We're going to get into one more gas law. Again, we're deriving from kinetic molecular theory, but, applying it in a new situation. First, there's not a lot of room for notes here, but let's just play these videos.
Hydrogen chloride and ammonia are gases at room temperature. They are highly soluble in water. Dissolved molecules easily pass into air from the concentrated solution. In the gas phase, molecules readily extend beyond the vessels. Ammonia and hydrogen chloride vapors are colorless, but when mixed together they form white smoke. Let's take a closer look and see where this smoke comes from. Smoke consists of small particles that we can't see with our eyes, but plenty of such particles form a plain gray background. Small crystals of ammonium chloride play the role of smoke particles in our case. Let's see how these crystals were formed.
Yeah, when you take concentrated hydrochloric acid and concentrated ammonia, both are solutions, but that means there's evaporation occurring, and those two gases create a solid, ammonium chloride. If these solid particles are made in the air as the gaseous particles collide with each other, and so it makes smoke, these tiny particles that float around. I do want to show now, to piggyback off of that, a separate experiment where it's done in a much more controlled fashion.
In this diffusion experiment, we're looking at the diffusion of HCl gas and ammonia gas. We have concentrated solutions of HCl and ammonia on a cot in the tube. The HCl and the ammonia escape from the solution. The gas travels down the tube. When the gases come together, they react to form solid ammonium chloride, which forms a white solid.
So that's interesting. When you do this in a closed environment, instead of the first video where you see smoke everywhere, you can get a very controlled environment where the particles, this only happens when the particles interact with each other. So you have a case where the ammonia is traveling from the right to the left because of diffusion, and the hydrochloric acid, the HCl particles, are traveling from left to right. So these two sides are both filled with air and those gases, and only where they meet in the middle is where you see the solid, except they're not meeting in the middle, they're meeting closer to the HCl. So what's up with that? Before I get too far into that, I did want to take a second to talk about effusion versus diffusion. The law we're talking about today concerns effusion. What you just saw in the tube was diffusion. It turns out that, they might have slightly different formulas that describe them, diffusion being a little bit more complex because usually diffusion happens not into a vacuum but into air. So there was that air to contend with. But in this case, even with that demonstration, the idea stays the same. Particles will end up spreading. In general, they will spread out and you'll get a gradual mixing effect of particles over time. That's not the same as effusion, but it works in largely the same way. As long as the air that's present between the two, HCl and the NH3, is a constant, we can still use the effusion math to describe what we're seeing and get an idea. Effusion is slightly different. If you want a good thing to picture for effusion, it's like a balloon. The idea that all the gas is coming out one hole instead of going in all directions. There is such a thing I did want to mention as solid-solid diffusion. It's rare, but if you've ever made golden or brass pennies, that's where it comes from. It's a very fun experiment to do. So let's pick apart, this whole process. The idea here is that this ends up further to this side than it should. So the synthesis reaction occurs at the interface. And so the information of the location, right, the idea, like I said, the closer that this reaction happens to one side, we can assume that those particles are slower. The idea is that they're going to be meeting and they're going to be going together. If they travel at the same speed, you'd see that line form right in the middle, but it doesn't. It shows up where they meet. But here's the hard part. You can very definitively see that the HCl particles are moving slower than the NH3 particles. But they're in the same tube at the same temperature. And temperature is average kinetic energy. So I'm a little confused. If they have the same kinetic energy, I think we have to look a little bit closer at what kinetic energy actually means. The formula for kinetic energy is shown here. 1 half mv squared, where m is mass and v is velocity. So to dig into this, we can say, well, hold on a second. If the average kinetic energies are the same, then the kinetic energy formulas have to be equal. We can plug in some information. I don't really know what the velocity is, but hold on a second. Let's work with the variables first. First things first, I see a 1 half on both sides, so we can just multiply everything by 2 and get rid of that. Mathematically, I usually so I'm stuck. Usually I'm a really big fan of having, the ammonias on one side of the equation and the HCl's on the other. That doesn't seem to help me any. I don't think this gets me anywhere. So instead, let's try to put the masses together and the velocities together. You know what? I was never really a big fan of square. Well, I'm stuck. Again, I'm stuck because I like squares, but I don't think this is also super informational to me. But if we do take the square root of both sides, we get this. The relative velocity is equal to the square root of the mass of the hydrochloric acid divided by the mass of the ammonia. So you'll notice that the ammonia is on the top on one side and on the bottom on the other. That's super important to this working. But this is Graham's law. If we were to put it into words, the relative rate of effusion is equal to the square root of the reciprocal of the ratio of the masses. That's not really good in words. So let's try putting some numbers in here. For the masses, I don't really know what the mass of a particle is in grams, but I can put like the molar mass. Since we're dividing, a lot of these units are going to disappear anyway, so it's just relative. For the mass of hydrochloric acid, we're going to say 36.5. For the ammonia, we're going to say 17. The reason I can pick whatever units I want is because they're going to cancel, and so when we divide our rates there, I get about 1.465. I'm not rounding appropriately, but you know what? This number helps. And if we wanted to round appropriately, I guess we'd call it 1.45 or 1.47 or even 1.5. 1.5 would be easy enough. The velocity of the average ammonia particle is equal to 1.5 times the average velocity of the HCl particle. Now that makes sense. That there tells me that the velocity of the ammonia is always faster, or on average faster. And if we were to take out a ruler and measure, this line where they meet seems to be roughly at the 40-60 point, which is consistent with a 3-to-2 ratio in the velocities of the particles. In other words, to really distill this down, small, light particles with low mass travel at a fast rate compared to heavier particles as long as the temperature is the same. So that's basically Graham's law in a nutshell. Again, similar to Dalton's law, this is another one that feels like it makes a little bit more sense if we use it than if we just try and talk about it. So again, we've got, we can use the word rate. We can use the V for velocity. We can do whatever we want. I've seen it referenced this way too, using rate and molar mass instead of velocity and mass. If we want to use this here, I'm just putting in A and B for now. But since we were told in the problem that these have names, right? One of them is hydrogen. Let's call B hydrogen. I think that's going to be B a little nicer for us. Remember that hydrogen is a diatomic. We also know that the rate is 50 over 1. Remember that it says 1/50th as fast as hydrogen. This means that to translate that means that particle A is traveling 1/50th the rate of hydrogen. Or A over H2 is 1 over 50, so the 50 is paired up with the hydrogen, that's why I wrote 50 over 1. So at this point, I don't need this part of the equation. And I know what the molar mass of hydrogen is. I can put a number to that. So again, then algebra takes over. If we want to isolate the molar mass of substance A, we square both sides. So we get the molar mass of A over 2 equals 2,500 over 1. We multiply over, and the molar mass of A is equal to 5,000 grams per mole. I didn't say that it was realistic. I'm just solving the problem that's in front of me. For another example, we've got two substances that we do know. This one's hydrogen, it's H2. This one's sulfur dioxide, that's SO2. So you see escape through a porous container or effuses. These are the words that are going to clue you in that we're using Graham's law here. Got rate of hydrogen. How much faster does hydrogen? So I like putting hydrogen on the top in this case. And rate of SO2. And that's going to be equal to the square root of the molar mass of the SO2 over the molar mass of hydrogen in this case. So sulfur is about 32, oxygen is about 16 each, so that's 64 over 2, which is going to be the square root of 32, and so that's between 5 and 6. I'll grab a calculator. It's about 5.7. So this tells me that hydrogen will diffuse out about 6 times faster than sulfur dioxide. This is a big explainer for why helium balloons tend to deflate. And they definitely deflate a lot faster than they do like air balloons. And the helium balloons will deflate because the helium can get out. It's very light. It's a small particle. It diffuses and effuses a lot more quickly than other heavier gases like nitrogen and oxygen. Another application of this, I love telling this story. The earliest attempts to refine uranium involved using Graham's law. How do you purify, how do you isolate an isotope? With uranium, there are two major isotopes that exist, 235 and 238, the two isotopic masses. 238 is about 99% of all uranium. 235 is the isotope that is used in nuclear power plants and nuclear bombs. For use in nuclear power plants and bombs, you need a percentage of at least 3%. You want to be up closer to 10 if you want to use it in a bomb, but 3 or 4% will work for a nuclear power plant. So how do you increase the percentage of 235 in your sample? I mean, I guess you'd need to remove certain isotopes, but we don't have the technology to pick out one atom. So what scientists did was they reacted the uranium with fluorine to make uranium hexafluoride. And that substance can go from a solid to a gas at a reasonable temperature. I don't remember the exact temperature. I want to say it's around 400 Celsius or something. It's definitely a lower temperature than turning uranium itself into a gas. And then they set up several of these chambers with pinholes to exploit Graham's law. The idea being is that if you have both in one container and you open up a pinhole, the lighter particle will end up transitioning into the next chamber over at a higher rate. And so over time, the concentration, or I guess initially, the concentration of the lighter particle will be much higher than what you started with. And what they did was they set this up, and then they had like miles of these chambers where they just opened the door one at a time. And by the end of several miles, because the only mass between these particles are massive, the total mass here is like 300 grams per mole. So the difference is only 3 grams per mole between them. So it takes several miles, but by the end of that, they had a sample where it was more 235 than what we started with. You collect that sample, you turn it back into a solid, you decompose it to get the fluorine back out, and then what you have is uranium that has a higher percentage of 235 than it does occur naturally. So it's like a neat little way that this actually was used in human history to accomplish a goal. Thanks for watching.